Hello, everyone. My name is Adrian Lucy. I'm a finishing graduate student at Columbia University, and I'm here to talk about symbiotic stars, their accretion disks, and their connections to other accreting systems. This work, a lot of the work that I'm going to talk about, would not have been at all possible without my many collaborators who I list on the slide here. And I want to especially acknowledge my debt to the staff at the South African Astronomical Observatory and Las Cumbres Observatory, the network sites at Siding Spring and Sutherland especially, and who kept enough telescopes working enough of the time during the pandemic that I'm going to be able to finish my thesis, among other things. And I want to also especially acknowledge my collaborators who observed from the Cape Town control room during the pandemic, including David Buckley, Hans Breitenbach, Stephen Potter, and Binish Paul. And if you hear purring or meowing or other eldritch noises throughout this presentation, there's literally nothing I can do about that. Gracie is here. She's choosing to be off camera, but there's nothing I can do about anything that whoa, see, for example, she just rolled over and knocked my camera away 6 inches to the right, but here we are. And here's a symbiotic star. They are wide binaries in which a cool giant accretes onto a more compact companion, usually a compact object, and usually a white dwarf, at least in the known sample of symbiotics. And the cool giant can generally be anything from a G through M star with luminosity class 1 through 3, but maybe classically you'd say it's usually an M giant, luminosity class 3. And the light from the accreting white dwarf, sometimes the light of the accretion disk, sometimes the light of nuclear burning on the surface of the white dwarf, illuminates the dense wind nebula of the mass-losing red giant, often resulting in an emission line spectrum superimposed on a red giant spectrum. So you have this cool component coexisting with a hot component, and that's why it's called symbiotic. Now, sometimes there are more stringent observational definitions relating to the presence of high ionization emission lines, but I'm going to stick to the physical definition, where a symbiotic is anything where a cool giant detectably accretes onto a more compact companion. And later I hope you'll see why I find that physical definition more useful in my work. But I think it basically comes down to caring more about the accretion disk than I care about the white dwarf or the nebula. So symbiotics are analogous to cataclysmic variables, except that in CVs, the donor stars remain sequence-like, whereas here you have a red giant, and the orbital period is measured in years. And that means that the disk can, in principle, be larger in symbiotics than CVs, since there's more room for it in a wide binary. And the accretion rate is also typically higher by orders of magnitude, facilitated at least in part by the stellar winds of red giants, which intrinsically have high mass loss, even without a binary companion. And like other accreting systems, from young stellar objects to AGN, symbiotics can exhibit flickering, a superposition of multiplicatively coupled fluctuations in the flux. Here I'm showing amateur photometry of MWC 560, showing this flickering. It's a symbiotic star. We don't really know what causes it, but it clearly originates in accretion disks, and it can, for example, be modeled as variations in the mass transfer rate propagating through the viscous disk. It's technically not quite a random walk and not quite stochastic, but it's similar. Some authors, like Simone Scaringi, have argued that the same physical processes explain flickering as a universal phenomenon in all accreting systems. In accreting white dwarf systems, it manifests on timescales from seconds to hours, with the fastest timescales in the innermost disk. Now, virtually all of the thousands of known CVs exhibit optical flickering from the accretion disk. And in contrast to CVs, until recently, of the 300 or so known symbiotics in the galaxy, only about 10 or 11, depending on how you count, have been found to exhibit optical flickering. In known symbiotics, optical disk flux is usually overwhelmed by the light of shell burning on the surface of the white dwarf, which is left over from a previous nova, or sustained quasi-stably in a narrow range of accretion rate over white dwarf mass parameter space. Or it's overwhelmed by the light of the cool giant, if indeed a disk is present at all, which sometimes it may not be. Basically, the problems are, number one, that symbiotics secrete at higher rates than CVs, leading to shell burning. Number two, that red giants are more luminous than main sequence stars. And number three, that sometimes maybe accretion is taking place quasi-spherically from the ambient wind nebula of the red giant and maybe doesn't always form a disk. But when we can find them, optically flickering symbiotics with significant optical disk flux allow the accretion rate to be monitored over time, to offer quantitative constraints on their disk structure through the flickering properties. And I'm also starting to think that they might preferentially drive jets and fast winds. And because symbiotics are accreting at a higher rate than CVs, they're an important point of comparison for tests of the universality of flickering's physical causes. And the parallels to other accreting systems don't end there. Radoslav Zamenhof has pointed out that if you look at the two prototypical non-burning accretion-powered optically flickering symbiotics MWC560 and CH-SIG, their emission lines almost identically resemble those of the prototypical AGN Aizuki-1 if you broaden and scale them. And Radoslav has also used this to argue for extending the eigenvector 1 idea in AGN into the accreting white dwarf regime. But in any case, much like it's sometimes useful to think of black hole X-ray binaries as microquasars, it can sometimes be useful to think of white dwarf symbiotic binaries as nanoquasars, as Radoslav has argued. And indeed, I've found it really useful to make that comparison sometimes. Here I'm comparing various states of the flickering symbiotic MWC560 UV spectrum to a low ionization broad absorption line quasar and an iron low ionization broad absorption line quasar. The broad absorption lines in both cases are accretion disk outflows flowing into the line of sight at thousands of kilometers per second. And actually that's an Fe Lobel quasar with Balmer absorption too in the rest frame optical, which is not shown, which is a very rare subset of broad absorption line quasars. But the comparison is appropriate since MWC560 has persistent broad Balmer absorption. That's probably because densities in symbiotic red giant wind nebulae are typically up to 10 to the 8 to 10 to the 12 per centimeter cubed, comparable to the densities necessary to populate Balmer absorption in photoionized quasar winds. And this is similar to Voigt's idea for low ionization broad absorption line quasars, that they represent a young evolutionary phase where the disk outflows of quasars entrain an ambient shroud of dust and gas, which disperses to lower column densities once exclusively high ionization bells are observed. So carbon-4 and nitrogen-5 had previously been misclassified as other lines when these symbiotic star spectra were taken. But both me and Christian Koenigke had a background in quasars, and I had a background in Fe Lobel quasars specifically, so we quickly recognized that line IDs, the correct line IDs, and we confirmed them with a little atomic physics and logic. And a picture emerged where the wind had turned off, maybe after clearing some of the ambient medium with large-scale ejections of the inner disk. And as the high-density outflow dispersed, so too did the ion curtain. But a year or so after that outburst, the status quo returned, the dense outflow reformed, and the iron curtain came back, and you're left with this object that is the only persistent stellar mass analog to Balmer Fe Lobel quasars. And 26 years later, the accretion rate reached a similar peak for the first time, and we looked to see what the outflow in the disk would do. And basically, just as the accretion rate started its slow rise at the beginning of 2015, there was this high-velocity outflow burst that quickly stopped. And then when the accretion rate peak was reached in 2016, the high-velocity outflow abruptly turned on again, staying stable and feeding a growing region of optically thin thermal radio emission for several months until the accretion rate and the outflow velocity entered a slow decline from peak. And importantly, this whole time, the inner disk kept flickering with large amplitudes on timescales of minutes. And that's completely unlike what happened 26 years prior, when there were these unstable discrete ejections at twice the usual fast outflow velocity as the disk basically stopped flickering except for some variability on hour timescales. There are also a lot of ways to interpret this story, but the one I like is that in 1990, the inner disk was ejected, suppressing the accretion rate outburst, while in 2016 there was that burst of high velocity outflow in 2015, and then this nice stable fast outflow in 2016, like a valve letting off steam. And thanks to long-term secular trends, the accretion rate had generally been higher in the preceding decades than in the decades preceding 1990. So maybe the large disks of symbiotic stars might allow for viscous timescales of at least several years to govern the outflow driving mechanism, whatever that is. So basically, there's this long-term memory in the disk outflow relationship. More recently, by the way, telegrams and papers by Zamenhof and Goransky and others have shown that in, I think, late 2018 to 2020, the flickering has completely stopped and the outflow turned off. So the relationship between the disk and the outflow continues to be close, reminiscent of the situation in X-ray binary microquasars. Okay, so hopefully a picture is emerging for you that it would be great to have a large sample of symbiotics with easily accessible flickering accretion disks, with a wide variety of outflows that you could look at as a function of accretion disk properties, and maybe begin to answer the question of what kinds of disks can launch jets, and why can symbiotics launch spectacular obvious jets while CV jet signatures are so subtle, and why does MW560 have this outflow into the line of sight. And indeed, this is a very exciting time for symbiotic star surveys. So, for example, a lot of new symbiotics have been found through emission line surveys by Joanna Mikołajewska and Mizalski and several other people, both inside the galaxy and really excitingly in nearby galaxies like M31. Similarly, there's Ramses 2 with Rodolfo Angeloni and Denise Gonçalves and others, in which I'm a small part, which is a new narrowband Raman 06 filter on Gemini that's really effective at finding symbiotics with shell burning. And this will be able to find shell-burning symbiotics really efficiently in other galaxies without much need for spectroscopic follow-up. Here we're showing commissioning data on the southernmost symbiotic star, which I found using methods that I'll discuss in a minute. And Stavros Sakras and others have been developing this really interesting way of distinguishing symbiotics from isolated giants and other mimics using machine learning with just infrared criteria, which is really interesting. And on the other end of the spectrum, at the near UV edge of the optical, here's what I've been working on. I built a sample of hundreds of thousands of likely red giants in the SkyMapper Southern Sky Survey footprint with simple infrared color and luminosity criteria using 2MASS and Gaia. And the main point is that both known catalog symbiotics and red giants with emission lines in my follow-up spectroscopy of 220 outliers are mostly away from the locus of red giants, in the bluer regions near Aegean contaminants. Just a quick warning, if you're interested in doing something similar, that these are not the SkyMapper master catalog colors, since the pipeline throws away data in a way that causes a lot of scatter in the apparent color of strongly pulsating objects. So you have to reconstruct the colors from the full measurement table if you're working with variable objects. Now, looking for blue excess flux isn't so different from relying just on emission lines. But you'll recall that until recently, there were only about 10 symbiotics that have been observed to have optical flickering. And I've designed a search mechanism that so far has found 4 more, all previously unclassified stars. And it involves looking for variability between the 3 U-band measurements separated by 8 to 16 minutes that SkyMapper makes during a single main survey filter sequence, and then secondarily ranking candidates by their color outlier score, as discussed previously. And it worked. In my pilot search, I found 4 more symbiotic stars with unambiguous B-band optical flickering and follow-up photometry. Here's where they are in parameter space in SkyMapper. Optical spectra confirm the presence of an M giant accompanied by some emission lines, sometimes just weak Balmer emission and nothing else, that might not make the cut in previous surveys or even previous definitions of symbiotic stars. But here's the thing. You can see these 4 flickering away in B-band Las Cumbres observatory light curves here. And that's the new symbiotics in black and check stars in red. To double check, I've started comparing each target's light curve RMS to 40 check stars, and I'm finding that they're consistent outliers. And I've also got Chandra observations for the 2 on the right, and they both have hard X-ray detections from the accretion disk boundary layer. So we're really set up to start rapidly building a large sample of non-burning symbiotics with detectable accretion disks, which really opens up this regime of accretion as a thing to examine. Maybe we'll even be able to look at whether symbiotic disks structurally resemble protoplanetary disks, since Peretz has this idea that symbiotics could host second-generation planet formation. So it's a really exciting time to be working in symbiotic stars, especially if you're interested in accretion disks on any scale. Thanks for listening, and please do email me with any thoughts.